I'm Sagues Carracedo. I'm a PhD student at the Optical Client Center in Stockholm. And well, first, for starting with my presentation, I want to thank the NOT staff for this great opportunity to be here. I was a NOT student 4 years ago, and it's really a good experience. I know what astronomy is like from the very beginning of taking the observation. So I'm going to talk on behalf of the MAAT collaboration, which is this IFU and the GTC I will talk about. So first mention that MAAT, as well as meaning mirror slicer array of astronomical transient, which is technical version, also has a meaning in Egyptian mythology, which is this goddess, and that represents truth and justice, which is really pretty concept for collaboration as well. So I'm going to start first with this video. You can find this in the main web page. So the MAAT is a module, Integral-Field unit will be located at the OSIRIS spectrograph as a visitor instrument, and this has been is funded by four institutions in Spain, Denmark, Sweden, and also some accredited researchers in Salamanca and Durham University. So the IFS would use this mirror slicer technique to get this slice the image, and then as you can see in the video, and then it would disperse the image of each slice with this OSIRIS spectrograph, and then finally, thanks to the MAAT software, you would get as a final product a 3D data cube from which you can get spectrophotometry at each point of the field of view you're observing. Then you have target acquisition with no overheads and with better signal to noise compared than with long-slit from OSIRIS, as you are collecting all the photons. So this instrument is already past the preliminary design review in April, and it will give first light at the end of 2024. So here are some basic parameters of the instrument that you can also find in the white paper and on the web page. As I mentioned, and we saw in the video, it's a module on the OSIRIS spectrograph. It has a wavelength range it covers a wavelength range from 360 to 1,000 nanometers, so it have the UV parts. And a remark, something to remark from this IFU and why this is a unique instrument, I will be a really Hola? Better? Sorry. Thank you. Yes. So yeah, let me continue then. So the MAATs, if we compare it with other scene-limited IFUs in 10-meter class telescopes, we see that it is MAAT and the GTC would be pretty unique in the northern hemisphere. Also covering a wavelength range that is pretty unique. It's comparable to MUSE, but with a larger coverage in UV. So also to see how MAAT stands in the time-space or compared with other instruments and surveys going on, we see MAAT here, here in the middle of the charts that will start together with the Vera Rubin Observatory, providing interesting transients, also with short wave observatories online and other satellites flying and giving lights. So with the MAAT collaboration, there are a bunch of science cases that, the scientific goals are unlimited, but yeah, and we will be able to really cover all the different, observe all the different, go into the different transients and the science cases that are also going to be of interest during the time domain time of LSST. So also, like within the collaboration in the project scientists, where we have the science team, we have two groups, cosmology and transient and galaxies and nebulae, where we are working on papers to try to show the prospects of MAAT data, how we will contribute to transient science. And also there is developing on the spatial time calculator and the pipeline that will reduce data and the database. So when MAAT goes online, we have good predictions and great framework to have good data. So why on the GTC? This is just an example from simulated data from taken from this kilonova 17 GFO and the galaxy where it was found. So the simulated data is taken from Muse archival data. It simulates how MAAT would see, how MAAT data would look like. And you cannot really see, but I was trying to show a comparison with the Muse wavelength range. That is kind of here in the middle. MAAT can have this UV pi, which will be really important for some cases. So how can MAAT, how can they not be of interest for us? So MAAT, as I mentioned, would give we will have a spectrophotometry, UV and optical wavelength. And the NOTs, well, we have been talking about the NOT for all these days, and we will continue. We have this image polarimetry, near-infrared observations. We have, with this dipole FU alphas, also with NOPCAM, we have the near-infrared data. Also with NT, I understand we will do everything with the same instrument. Maybe we can do some rapid mode, or I don't know, do some kind of agreement to complement observations to contribute to the science cases we're interested in. So now I'm going to talk a little bit about kilonova, because it's what I have contributed to and what I know the most. So just to give you an idea, I'm sorry for this plot, a little bit busy, but I wanted to summarize everything in the same plot. Here on the top, I'm just trying to illustrate for some of you, if you don't know what a kilonova is or what it comes from. It's this explosion that rises from the merger of compact objects when one of the objects is a neutron star. At least one of them is a neutron star. So with these mergers produce radiational waves, emit radiational waves, and also have short gamma rays burst, and the kilonova, which is this emission, this expanded ejecta that we observe. And something very peculiar, or something important in the kilonova, is also that the geometry really affects the observations, because you have two different components with different opacities, and then the photons will be really affected by the line of sight we're observing. Also, these transits are very fast evolving. They evolve in days, and they go to radar wavelength very quickly. And they have also really interesting applications in cosmology, and also question states of dense matter and nucleosynthesis studies. So they're really interesting objects. And so what I wanted to show is that, so with MAAT, we're really excited about kilonova science, as we have also this UV part. So mainly for early times, we will be able to understand what's happening in this shorter wavelength. And this will help us also understanding the geometry of the system and different models. What is the composition? But then we have, after some days, then we will need radar wavelength to observe later times and help to understand the excess in the infrareds that we will have. Then also, if we can use polarimetry, we can also get some idea of the geometry of the system as the polarization changes depending on the component. There is also dust environments that we can study with NOT data and host galaxy characterization. So just mention that we have this paper on kilonovae where we want to study question state and H0 estimations with spectrophotometric light curve taken with MAAT. And I just put some plot here to show these are different models. So this would be Iranovi rising, assuming different question states. So I just wanted to show this to emphasize on the fact that having near-infrared data with the NOT would help us discern and infer better which kind of models we are might be when we do the modeling. What kind of physics is really behind the light cursor observing? And then regarding the H0, I chose to put this plot from a review paper that was published recently. MAAT is this orange line here. This is how well we can constrain the viewing angle with the traditional wave plus the MAAT data. And then here would be the orange one, how well we can constrain H0. This is comparing with not only optical data, but also with the GRB traditional wave only. So it's really competitive what we can do already with MAAT, but we believe that having extra data with the NOT, with a longer wavelength or polarimetry, we can also use it for constraining the viewing angle, the geometry of the system, and maybe having some interpolated observations that would help us also identifying the transients on time, so we can do the science when we need to do the science on point when we need to do. And that would be really an improvement in the science we want to do. So yeah, that's basically my conclusions, that MAAT is going to give us some unique opportunities and complete revolution in the time domain astronomy. And synergy with the NOTs are potentially going to give major contributions to the cases, science cases we're interested. I show about kilonova because it's the one I know about, but there are plenty of more things we plan to do with MAAT. Yeah, that's it. Thank you.